I am making a video. This is being recorded in the teacher workroom. Alright, we're going to do circuit analysis here. There's a beautiful circuit drawn already on the top. We're going to learn how to simplify this until I have just one battery and one resistor. Alright, first we're going to start with the easy part, resistors in series. So these are all just lined up nice and neat. Everybody's on the same line. Here you can just write one side as a positive terminal and one side as a negative ground. Alright, resistors, this is as easy as it gets. You just add them together. That's it. You can add, right? Then you can do resistors in series. Here's your equation. R total equals R1 plus R2 plus R to the nth. So let's say this guy was 10, this guy was 5, and this guy was 20. 10 plus 5 plus 20 equals 35. Hey, look at me. I can add. I can do resistors in series. So this is just the same as this. This circuit behaves the same as this one. They are identical to each other. Let's see if we can do this on our own. Doesn't even matter what the battery is. So here I got 10 and 20 and 30. So I say 10 plus 20 plus 30 gives me 60 ohms. So once again, this circuit behaves the same as this one in terms of overall power consumption, current that leaves the battery. There's only one path, so current goes all the way through the circuit to the end of the battery. It acts as the same. Alright, resistors in parallel. This is a little different. Alright, if students are going to lunch and there's only one path to take, it's going to take a little bit of time to get to the cafeteria. But if there's two paths, now twice the amount of students can get there in the same time. Resistors in parallel work the same way. What I'm doing is I'm opening up another branch that current can move through. So if I just have current labeled I normally leaving, now I can have twice the current that goes through two separate paths. So more paths in parallel will allow for more current to flow. Here your equation works like 1 over R1 plus 1 over R2 equals 1 over R total. So if each of these had a value of, let's say, 20 ohms, 1 over 20 plus 1 over 20 equals 1 over R equivalent. So 1 over 20 plus 1 over 20 equals 2 over 20. So 2 over 20 equals 1 over R. You flip both sides. So 20 over 2 equals R. So then R equals just 10 ohms. So this behaves the same as this in terms of how much current is able to leave the battery, come back to the battery, and this one resistor consumes as much power as both of these. The only difference is now the current has to split when it comes to this junction right here. So since these are equal, half of it's going to go this way and the other half is going to go that way. Alright, once again, here's my three resistors. It's the same process, 1 over 15 plus 1 over 15 plus 1 over 15. 1, 2, 3 over 15 equals 1 over R. Flippity flop both sides. R equals 5. So it's the same thing as just having this guy here with 5 ohms. Once again, since they're all equal, 1/3 of the current is going to go this way, and this way, all moving in the same clockwise direction. Alright, now we're going to combine the two. So now I have series and parallel together. So the best way to do this is to work backwards and always redraw your circuit after you find equivalent resistance. So I'm going to start over here with these two guys. So I go 1 over 30 plus 1 over 30 equals 1 over R. 2 over 30 equals 1 over R, so 30 over 2 equals R. R equals 15. So now I'm going to redraw my circuit. So this guy was 10. I just found this equivalent to be 15, and this is 20. Now everything is in series. There's only one path to flow through, so it goes 10, 15, 25 plus 20 is 45. So in the end, this big, huge circuit behaves the same as this one. The same amount of current leaves the battery, that comes back to the battery, and power consumption is the same. Now, once again, this individual resistor is going to eat more power. The current splits up as it goes through here, and we'll talk more about that. But in terms of circuit analysis, you've got all you need.